Let's take a look at question number 4 on the sample test. So problem number 4 says, give an example for each of the following. So part A says, two factors whose product is 5x squared plus 35x. So you would have to know what this language means in order to solve this problem. So a product is the end result of a multiplication problem. So 5x squared plus 35x would be the end result of multiplying two algebraic expressions. And what would those expressions look like? Well, if we ended up with 5x squared plus 35x, we're looking for two factors of this addition problem. So the first form of factoring you always check out is the greatest common factor. Is there a greatest common factor to each one of these terms, which are the pieces of an addition and subtraction problem? And you can see that both of those terms, those boxes, have 5. The number 5 divides 5, and the number 5 divides 35. And also, they each have x. They each contain at least one x. So 5x will be one of the factors. And then you represent the second factor by saying, what would I have to multiply 5x by to get 5x squared? And you could put an x in there. And then 5x times what gives me 35x? And that would be 7. So this is what you would do to answer this question. Here's your example of the factors. 5x is your first factor. X plus 7 is your second factor. Okay, the next one's a little more interesting. It says, give an example of a quadratic equation that has two imaginary solutions. So first of all, you have to know that a quadratic equation is an equation where the highest power you see is 2. And to have imaginary solutions, you're going to be trying to take the square root of a negative number. So we could get really fancy here and do a problem like number 3c. In our previous problem, number 3c was this equation. X squared equals 4x minus 7. And when we solved that in number 3, we got an imaginary solution. However, we don't have to get that fancy. All we have to do is say, let x squared equal some negative number, any negative number. It could be -1, it could be -5, it could be -49. All three of these equations would have imaginary solutions, and there would be two of them. So for example, this one, if we found the square roots of both sides, it would be plus or minus the square root of -1, which is plus or minus I. This one would be x equals plus or minus 7i, etc. Okay, so any of these equations here would satisfy the conditions for 4b. Okay, let's take a look at 4c. 4c asks us to give an example of a multiplication problem involving exponents that when we simplify it, our answer is 1 over x squared. That would be the answer after we multiply two quantities, two expressions with the same base. We just have to figure out what would we put up here for our exponents. Well, another way to write 1 over x squared is x to the -2. And we know that when we multiply exponential expressions, we add with the same base, we add the exponents. So now we know that something about our exponents. When we add them, we end up with -2. So we could have a variety of different answers here. We could say x to the 4th times x to the -6. That would give us x to the 4 plus -6, which is x to the -2, which is 1 over x squared. So, you know, we could do just about anything our little heart desired here, as long as that when we added those exponents, we get x to the -2. So as you can see, there's a variety of different answers here as well. Give an example of an integer that is not in the interval parenthesis -6, 4. Now, if you recall our interval notation, when we have the parenthesis, that's an endpoint of our interval, but we're not including it. So our textbook uses the parenthesis there, but most of you are used to doing this type of problem where you would put an open circle there. They both mean the same thing. Okay, so let's take a look at the rest of this. So this interval starts at -6 but doesn't include -6 and goes up to the integer 4, and it includes 4. So we put the staple there, the bracket. So this interval includes all of the real numbers between -6 and 4. And similarly, if you were using sort of the other idea of open circle and closed, you would do that and then shade everything in between. So you have to give an example of an integer not in this interval. So as you can see, any integer greater than 4, -6, or less than -6 would not be in that interval. So you could say something like x equals 12, x equals -10. You could even say x equals -6 because that's not in the interval. Again, there's a variety of answers for this problem. Okay, two complex numbers that are conjugates of each other. If you recall, conjugates look very similar, except one has an addition sign and one has a subtraction sign. So you could say something like this: 2 plus 5i times 2 minus 5i. Okay, so anything that has the form of a plus bi and a minus bi would be an example of this problem. All right, an absolute value equation that has no solutions. Well, what do we know about absolute value? We know that absolute value, the answer to an absolute value, is the distance from 0 to a quantity. So it's always positive. So if you set an absolute value equation equal to a negative number, that's not going to have any solutions. So anything that looks like this would be an acceptable answer for 4F. Finally, two sets whose intersection is empty. So if we had a picture of two different sets, they wouldn't overlap at all. There'd be no intersection. So you could have the set that had the numbers 1, 2, 4, and a set that had the numbers -5 and 10. And those two sets do not have any elements or numbers in common. So to write two sets, remember you have to use your little curly braces. So you could say one set would be 1, 2, 4, and your other set would be curly braces -5, 10. All right. Sometimes if you want, you can always give these sets a name, like a big capital letter like this if you want, but it's not necessary. What's really important is that when you list the elements in your set, you make sure you include your set symbol here, which are these little curly braces. Okay, that's question number 4.